Okay, in this video, we're going to attempt to cover all the key ideas and types of questions for the standard level material of kinetics, which has to do with the topic of reaction rates. So I cut this out from the IB syllabus. Essential idea of kinetics: the greater the probability that molecules will collide with sufficient energy and proper orientation, the higher the rate of reaction. This is the list of things that we're going to cover in the video as quickly as possible. Species react as a result of collisions of sufficient energy and proper orientation. That right there is more or less the collision theory in a very concise form. So collision theory states that in order to react, reactant particles must have the proper orientation. They must collide. Obviously, that's the first part. So they must collide, and they must collide with the proper orientation. And they need to have sufficient energy. And the sufficient energy is that they need to have sufficient energy to overcome the activation energy. So this is a little bit sloppy, so let's fix this. Shrink it down. So these are the points of collision theory. The must collide one is sort of one that you could leave out because it's kind of obvious. If the theory is called collision theory, the particles must collide. But if you're talking about reactants, in order for them to reaction to take place, the reactant particles have to collide, they have to be in the proper orientation, and they have to have enough energy to overcome whatever the energy hurdle is for that reaction. So, like, to break the bonds apart and get the reaction going, that's the activation energy. The activation energy is often abbreviated as E sub A, energy of activation, and it's the minimum energy required to bring about a reaction. Okay, so those are the points of collision theory, and you've probably covered them before, but that was just to make them a little bit clearer. Theory is what that's called. Okay. Other things: the rate of reaction is expressed as the change in concentration of a particular reactant or product per unit time. So the definition of rate of reaction is either the increase in a product concentration per time, or it's the decrease in a reactant concentration per unit time. Those are the technical units to measure rate of reaction in. You can also follow how quickly a reaction is progressing a little bit more indirectly by measuring mass, volume, or color, something that we'll look at further. Here's the activation energy definition. Activation energy is the minimum energy that colliding molecules need in order to have a successful collisions leading to a reaction. More or less what I said down there. And catalysts decrease activation energy, and therefore they increase rates of reaction without themselves being permanently changed into something new. We're also going to look at graphs, and we're going to describe the effects of these various factors. So I'm going to skip the list now and go on to things that we need to worry about for IB questions. So probably the most important thing about kinetics, because I think it's a pretty intuitive topic, is the wording. The wording in your mark scheme answers, which we know is always important, but since it's pretty simple otherwise, it ends up being quite important for this chapter. So if we keep these points on the left, those are the three ideas from collision theory, that we've got to have particles must collide, they must have proper orientation, and they must have sufficient energy. When we talk about factors that affect rates of reaction, it's very common for you to predict, one, how will they affect the rate of reaction, and then to explain why. Right? So changes in, you probably already all know from previous years of science that increasing the concentration of reactants will cause reactions to increase. If we can increase the surface area of solid reactants by chopping them up or grinding them up into smaller pieces, we expose more surface area. That makes reactions go faster. It's pretty obvious that increasing temperature makes reactions go faster, and if we increase the pressure of a gas, we can make the reaction go faster, because increasing the pressure on a gas means we're going to shrink the volume of a gas. It's going to shove all the particles into smaller spaces, and that essentially means we've increased the concentration of the gas. So concentration, surface area, temperature, pressure, those are all factors that affect rates of reaction. but they all tie back. So, I mean, predicting the how they're going to affect the reaction is pretty intuitive. When you explain why these things affect rate of reaction, you got to use the right wording. So the wording for all of those things, why did these things affect the rate of a chemical reaction? It's because they increase the frequency of the collisions between the particles. The common mistake is to say that they increase the number of collisions. But number of collisions is a little bit tricky. If you're talking about like total number of collisions, well, if you don't change the moles of reactants, then actually the number of collisions in total doesn't change. So like increasing temperature doesn't change anything about how much you're using. It doesn't change the total number of collisions. It changes how fast they happen or how often they occur. So you need to watch out for this language where you say number of collisions. It's something they look for, and it's something that's wrong. So you need to say the number of collisions per time, or you can say the frequency of collisions, which means the same thing. So putting more particles into the same space by concentration increases or pressure increases, that causes greater frequency of collisions. Surface area exposes more particles, and therefore collisions occur more frequently. And temperature makes particles move on average faster, and therefore they bump into each other more often. The two other ways to explain why a reaction rate goes faster have to do with the energy. So they have to do with the third bullet point of collision theory, which is that particles have sufficient energy to overcome the activation energy. So to make a reaction go faster, you can either make the particles have more energy, which is what temperature does, right? So if you increase the temp, the particles have more and more average kinetic energy, which means more particles are going to have sufficient energy to overcome the activation energy. So you notice that for temperature, there's actually temperature increases reaction rates for two reasons. One, because collisions are more frequent, and one, because the average particle has more energy. The second reason is considered to be the more important reason for temperature of the two. They both play a role in why the rates go faster, but this energy reason is considered to be the more important factor. Another thing you can do to make reactions go faster is add a catalyst. Catalyst is some substance. It could be a piece of metal. It could be acid. It could be an enzyme. It's some other substance that you add. And what it does is it provides a lower energy pathway for the reaction. So it lowers the energy requirement. It lowers the activation energy. Over here, this is what you could call an energy profile for a given reaction. We've already looked at them in energetics. You've got your reactant side over here. You've got your products over here. And the change in energy is that is the delta H between the two lines, and you've got the energy hurdle, the activation energy. Well, with a catalyst, you get a new energy profile, and you get it in terms of a lower hill. So the hill has been lowered, the hurdle has been lowered, and therefore a lot more particles have sufficient energy to overcome the activation energy. So going back through the wording, you can, for these factors, point out that the frequency of collisions is affected, either increased or decreased, depending on what the change has been. With temperature, you can refer to the average kinetic energy of particles changing and how that affects the number of particles that have sufficient energy to overcome the activation energy. And with a catalyst, you can talk about how the activation energy is lowered and therefore more particles with sufficient energy to overcome the activation energy. So notice that for reasons 2 and reason 3, the increase in temp or a catalyst, you could really end up saying the same reason in the end is that more particles would have enough energy to overcome the activation energy. So that's kind of the theory part of it. This is the questions you get where they ask you what's going to happen to the reaction rate and why, and that's the wording that you'd use to explain it. Actually, measuring reaction rate, there's lots of different variables that get used to measure reaction rate, sort of indirectly. So for reactions that produce gases, so you can measure directly the volume of a gas. You can also measure how much mass is lost over time, because if you're making a gas, it's going to lose mass. Or you can measure the total mass of the reaction vessel, which should go down over time if you're making a gas. One I left off, and I'll add in here, you can also use a pressure probe and measure the pressure of gas in a sealed off container over time. So different ways to measure the same thing, but these three really only work if the reaction produces gas. And that kind of is obvious, but just thought I'd point it out. If you have a reaction that's all aqueous, particles and reactants and products, well, you're not going to have anything leaving really, so none of these values are going to change. So those are some common ones to measure. If you have a color change, you can monitor how much of a particular wavelength is being absorbed over time, and that should either increase or decrease depending on if the reactant or product is what you're looking at, the color that you're looking at. You can sort of measure concentration directly if you do titrations on a reaction mixture at different times, or if you measure conductivity changes, if there's a change in the number of ions in the solution. Not as common. We're not going to do any this way in this class. And then one final thing that's a bit odd is you can look at reactions that produce a very distinct color change, but that color change sort of happens all at once. So you can't continuously monitor how the color changes. You can only time how long it takes for a reaction to happen. And that can give you a sense about the average rate of reaction for that type of reaction. The top ones, these three, are really the most common that show up in IB exam questions. So a key thing to remember about reaction rates. For reaction rates, the rate is fastest at the beginning, and that's because that's when you have the most concentration of any of reactants. They're always highest at the start. As soon as they start reacting, concentration starts to decrease, and for this stated reason, that means the frequency of collisions goes down and down as the reaction proceeds. So reactions start off fastest, and then they get slower and slower. Over time, the reactant concentrations should go down, and product concentrations should go up. So this graph sort of represents a simple chemical reaction where you think of the reactant as being totally used up and product as being totally formed. So you don't have any product at the beginning, you have all reactant, and this is how they would change over time. In reality, a lot of chemical reactions actually reach equilibrium. So they don't go fully to completion, the reactants don't go to zero. And we'll have another chapter where we talk about reactions where when you're done, you still have a fair amount of both reactants and products in the mixture. For now, what we really care about is just the shapes of these curves, okay? So remember that the shape is super important because it's always got to be steepest at the beginning, and then it's going to get less and less steep and eventually plateau when the limiting reactant is used up. So the flat part means that the limiting reactant is used up, right? Whichever that is. And you have the steepest slope at time equals zero, right initially. Okay. Other key things to take away is that the slope represents your reaction rate. It's the rate of change of the variable that you're looking at. And the slope of the tangent line at a given point is the instantaneous reaction rate at that time. So sometimes you'll take the slope, you could take the average rate if you wanted to look at time zero, and you wanted to look at what's the average rate from time 0 to time 20, and you could say just rise, right? Here's rise, here's run, and you could calculate what the average rate is, and do it like that. So this represents the average rate right there, okay? Write it in, that's the average rate. Okay. But the instantaneous rate, if I want to know what is the rate right at this point B, then I try to get a tangent line, right? And I figure out what is the equation, and therefore what is the m value, y equals mx plus b, what's the slope value here? And that's the slope of the tangent line at a given point. That gives you the rate right at that time. Usually what we care about is the initial rate of reaction. So we get all this data, but we just try to find what is the slope right at time 0? What's the tangent line right at time 0? And that's usually the rate that we care about. A lot of questions have you annotate graphs. So they'll give you a curve like this, where this is the volume of gas being collected over time. You can see it sort of takes this characteristic shape of increasing more quickly at first and eventually plateauing. And then they'll say, well, what would it look like if we increased the temperature? Well, if you increase the temperature, it's going to go up more steeply at first, but you need to make sure that it ends at the same eventual height. So I'm doing my best with this. Okay, so increased temp has to be steeper at first for the faster reaction rate, but increasing temp doesn't affect the moles of limiting reactant, and therefore it should create the same amount of gas. So this is the only real one to watch for with the graphs is changes in concentration and sort of changes in volume for aqueous reactions. Reason being, you should know that N equals CV. So if you change concentration or volume, you have the potential to change the moles. Most of the time, what they'll do is if they double concentration, for example, they usually half volume. They don't always do this, but that's what you need to sort of watch for. This equals the same moles, and so if this is what we did, then I'll do that one in blue. It would look just like the temperature one. Because we doubled concentration, it would go up more quickly, but we'd end at the same height. Now, if they did, if they did same concentration and half volume, right? Now we'd have half the moles, right? So it would go up at the same initial rate as the original line, because it's the same concentration, but then it would level off at like 35 because this is at 70, so we should try to be pretty precise that this is where it's going to end. So you've got to watch out with changes in concentration and volume because they can affect not only the initial slope, but also where you end up. Increases in temperature or catalyst, those don't have, or surface area, those have no effect on moles, so they should all end at the same height. Before we move on from graphs, just to recognize that some variables decrease over time, and that one specific one would be like total mass. If we're doing the gas example, over time, you would expect that the total mass of the reaction vessel would start off at its highest, and it would level off. Probably is never going to reach zero because the beaker weighs something, but it's going to look like this. And so any slope values you get are going to show negative slopes because the mass is decreasing. You should note that if you want to measure change in mass as your variable, don't use this variable for hydrogen. If hydrogen is your product, because the mass is too small to show a noticeable difference in the mass for most balances. So this works pretty well if you're using producing carbon dioxide or oxygen as your gas. You can use these variables, but not hydrogen. Okay. Final topics in SL have to do with what's called the kinetic molecular theory of matter and the Maxwell-Boltzmann distributions. So kinetic molecular theory talks about how particles in any state of matter have sort of kinetic energy and random motion. And the idea is when you look at a substance, whether it's solid, liquid, or gas, they have kinetic energy. There we go. Let's fix that. They have kinetic energy, but they don't all have the same energy. If you had a gas, some particles are moving very, very fast, but some particles might be getting collided into in such a way that it nearly stops them for a split second in time. So what we really care about when we talk about particles' kinetic energy is we care about the average kinetic energy. That's really what's going to matter. And the average kinetic energy is directly related to temperature, or absolute temperature, which means the Kelvin temperature. Okay? So just to keep in mind that temperature has to do with an average kinetic energy, and recognizing that not every particle in a mixture has the same speed, has the same energy, which is why when you mix two things, and they're at a given temperature, only some of the particles react right away because only some of them have enough energy at the beginning to overcome that activation energy, and some are not moving fast enough to do so right at that instant. Right? Another thing in this kinetic molecular theory is that as you go from solid to liquid to gas for a given substance, you're going to be increasing the kinetic energy of those particles on average. I think that's fairly obvious. You're also increasing potential energy as you go that way as well. But just for this topic, it means you have to increase their average kinetic energy as well. The particles are moving more quickly. Something called the Maxwell-Boltzmann distribution essentially takes a look at this graphically. And so it's sort of like a funny shaped bell curve. And it's just a way to represent this idea that it's the average kinetic energy. Not all the particles have the same kinetic energy. If this y-axis is number of particles and this is energy of particles, kinetic energy of particles, note that most of the particles have energy towards the middle, towards the average value. But at any given temperature, there's going to be some particles that are very slow, down here. There are going to be some that are very fast. And then these guys are close to average KE. So sort of the top of this curve, or the middle energy value here, is essentially the temperature. This really represents this temperature for whatever this graph, whatever substance we're talking about, right? So the average value is the temperature. So somewhere ballpark around the peak, this is sort of like the temperature, but even though most of the particles are around that kinetic energy, some are moving very slow and some are moving very fast. And only the particles that are past the activation energy, so if you add in a line that represents the activation energy amount, the sort of hurdle here, right? Only the fast particles, the really fast particles, are the ones that have enough energy to react. Okay? So why does a catalyst increase the rate of reaction? Well, a catalyst lowers activation energy, right? So if we add a catalyst, it's like we move the hurdle down. Right? So this is it's hard, EA. Probably shouldn't have chosen this one to write in, but this one is with catalyst. Okay, and so EA with the catalyst is a lower activation energy, and now you've got all these particles here that have enough energy to react now as a result of that adding that catalyst. So more particles have sufficient energy to react. Similarly, if you look at a Maxwell-Boltzmann distribution, and you change the temperature, you'd be expected to know how the curve shape should change with that change in temperature. So if you look at the dark blue one, that's sort of like a room temp, normal shaped bell curve. As you increase the temperature, you should see the peak of the curve, which the peak is sort of equal to the average, which is equal to the temperature, right? That should shift right. Right? If we're increasing temperature, then the peak needs to go further to the right, further towards higher energies. Okay? I'll rewrite over this that for us, for our purposes, we're talking about energy here on the y-axis. And I will white out that square, check it, boom, boom, boom. Where'd my thing go? There it is. There we go. We don't have to worry about that guy anymore. Okay, so the peak is essentially the average, which is essentially the temperature. So a shift right represents an increase in temperature. A shift left would represent a decrease. Okay. Now, if you're assuming that the number of particles in your substance hasn't changed, the reason why as you go to the right, the peaks get flatter, not as high, is because you're trying to represent the same total number of particles, which means that the area underneath the curve needs to stay the same, because the area under the curve represents the total number of particles. So as the range of speeds, the range of energies gets wider, there's fewer and fewer particles at each one of those speeds. The range of speeds gets broader. So the area under the curve stays the same as the peaks shift left or right. So when you get colder, the peak shifts left, so the average is less. This is the lowest temperature, 100K, and the range of speeds is quite narrow. But it becomes a very tall peak because a lot of particles are moving at that now smaller range of speeds. And the total area under that curve is the same as the total area under the dark blue curve or the purple curve. So as we shift to the right, we see that the peak is shifting to the right, but we're also seeing that the peak is going down. So the peak lowers, keep total area, which is number of particles, the same under the curve. Okay? If you add a line to represent activation energy on here, you can see that the higher the temperature, right, so if that represents activation energy, then the higher the temperature, the more particles that are now past that thing. So with the red curve, you've got the most particles with sufficient energy to react. Purple, there's less than that. Blue, there's very few that have enough. And light blue, there's no particles that have enough energy to react and overcome the activation energy. So on these Maxwell-Boltzmann distributions, you could be asked to just draw a Maxwell-Boltzmann distribution, labeling number of particles and energy, starting at the origin, bell-shaped curve, and not ever quite touching the x-axis here, adding activation energy with a catalyst, and discussing connecting between the graph and why that makes reactions go faster. You could also be asked to draw two curves, one for regular temperature and one for a different temperature, and you'd be expected to make the peak move left or right and either get taller or shorter depending on what the change was. And again, adding activation energy and discussing why changing temp affects reaction rate. And that is Kinetics SL in one video.